Well, hello. You're watching Math Head. All right, so in this video, I want to start to build the intuition behind portfolio creation. Okay, so this is going to be a finance-based math video, and it's going to be about the math behind portfolio creation. I'm not saying that the math behind it is correct. I just want to identify the math behind the most widely used portfolio creation theory, which happens to be modern portfolio theory as of now anyways in 2021. So Math Head, this channel is all about the mathematics of everyday life. Now, you might be saying, oh, well, I work at Subway and I don't even have a portfolio, so how does this apply to me? Well, you should have a portfolio, possibly, but one thing's for sure, math applies to you because that is how they allocate your savings account or your retirement accounts and different types of things like that. So if someone is handling your retirement accounts and you have an actual, good paying job and it's not, it's a corporate job or it's some kind of job that's not like Subway or Bag Boy or Girl or whatever, and you are getting some kind of deposit in a retirement account, a 401k, or any of that stuff, that makes it extremely important to understand if, what are they doing? How are they picking the stuff that's going into my portfolio? What are they relying on? So this math is applicable to everyone, especially if you have a retirement account or if you've been thinking about getting into investing or any of that stuff. These types of questions are very important to you, not just business people and this and that. And this is the number one reason. If you want to be totally reliant on someone, then yes, don't learn math. But if you want to take your life into your own hands, and this sounds like a ridiculous like Tony Robbins thing, but I'm 100% serious. If you want to take your life into your own hands and understand the world at a higher level, then mathematics is what you need, because for some reason the world is basically able to be used, mathematics is able to be used to model the world pretty closely. All right, so with that said though, you have to be extremely careful, and that's why it's important to build the intuition for these models that they use in portfolio creation and separate the model facts, the facts behind the math, and reality. Okay, so we're going to talk about that in this video. So right off all this stuff, okay, all of these things, we go from step 1, 2, 3, 4, step 5, and then basically step 6 is this modern portfolio theory. Right away, step 1, if you're thinking about what assets to invest your portfolio in, what kind of investments you want to make, it might be a reasonable decision to think, okay, what would I expect to make? Like, what amount of money is this thing going to pay me, or is this thing going to be valued at? Okay, so right off the bat, you think, oh, well, perhaps, the expected return I could use or something like that. So there's a math formula for that. It's a guess, though, and this is one of the first things that you'll see in the assumptions. This is an average value, okay? So it's a mean calculation, which means that you have a set of values and a probability of the return of each of those values. Now, the probability of this amount happening, and then you add all those up, and the total is the expected return. Now, probability works basically like this. It's a number of something happening over the total number of possibilities that it could take on. For example, the roll of a die. Okay, you have 6 sides, so the probability of getting one side generally in the long term, that's another factor that you need to consider, is going to be 1 out of 6. That's the best guess. Are you going to roll the die and have, strings of 2, 2, 2, 2, 2, 2, 7, 7, 7, 7, 7? Yes. So that's another thing to consider. But So we would start, developing our intuition for the perfect portfolio at expected returns. And the probability, when you have a sequence of data, time series data, like the price, the closing price at every single day for a stock, let's say, for example, or the price of a house over the year or over a few years, then you're able to calculate this the same you would calculate the median of, or not the median, excuse me, the mean of something. So if it's 1, 2, 3, 4, 5, you have 5 values, that goes in the bottom, the denominator, and you 1 plus 2 plus 3 plus 4 plus 5 on the numerator, all right? And there's actually a proof that that is n times n plus 1 over 2. So in this case, it would be 5 times 6, which is 30, divided by 2, which is 15, and then divided by 5. So that whole thing would be expected value of 3 if you had 5 values, 1, 2, 3, 4, 5. All right. I'll make a video on that too. So that's a cool little proof. The expected return of multiple assets. So now having one asset, you might think, well, it goes up and goes down. Maybe I can do a little better by having 2 things in my portfolio, like hedging, if you've ever heard that term. One would go up possibly, and then hopefully the other one goes up too, but maybe there's some difference, like one's a technology sector and the other one is a food sector or something, and one goes up and they both go up at the same time in good markets, but then say the technology sector is having a dive, but food, everyone's got to eat, that still goes up or something. It hedges your position, it stops your losses basically. So then you could naturally arrive at, well, maybe let's calculate the expected return for multiple assets. And then that becomes this formula with this crazy little summation, but it's nothing more than adding every expected return of the assets. And you think, okay, yeah, that's pretty good, but then this is true when you have 100% allocation in each asset. So then you might think, okay, well, would it be better to hold 70% tech stocks or, and 30% food stocks, or how would I do that? And so you might come to the conclusion that, well, I need to create some kind of allocation based on some measure of a fluctuation or something. Like how, if the tech stock fluctuates a ton, and it goes, the expected value is $3, but it fluctuates up and down. You could have like, $0 up to $7 or $20 or whatever. But then the food stock stays pretty consistent. You might think, well, maybe I'll measure the amount of fluctuations or the difference between, where it goes and the mean value. And really, we're not going to get into this now, but a side note, when you're looking at negative outcomes, when you're looking at portfolio creation, you shouldn't really care how high it goes, if you're risk averse, if you don't like taking on risk, because that's not really risk, that's reward. You're getting a ton of money higher than your expected return, that's reward. But these calculations are double-sided, like the variance. It just depends on the difference between the value you looked at in your time series and the mean value that you calculated. That's what variance is. It's symmetrical about the mean. So really, it's an incomplete picture, but that's what we'll use for this to build this intuition, and then we can refine it in later videos, all right? So now we've got this expected return of multiple assets. Well, we want to know how much of each asset we should hold. Because like I just said, there might be some like optimal mix or something. So then we just do the fancy notation where this is the total investment amount we have, 100% of whatever. If we have $1,000, that represents our 100% of investment money. And the sum of the weights just means that like we're going to put $50 in this stock, $20 in this asset, $100 in this asset, and then we're going to have 100% of our money spent, or we'll, and even one of these assets might be cash. So that would still account for the weight, the amount of money we're going to put in it. All right. So the total expected return for our portfolio then becomes this weighted expected return for each asset. And we might think, okay, yeah, that's awesome. This is how much I could make. But we haven't considered that fluctuation, that variance yet. So since this isn't the entire picture, we need to measure risk, basically, for lack of a better term. But risk in this case is difference or deviation from the mean. So if your mean price is $3 and it goes down to $1, that's a difference of $2. So that's going to be a risk. You're risking losing your money based on historical data. Okay, so like I said, it's symmetric. So we're counting the risk. We're counting the values above the expected value as risky too, which is kind of stupid. But we'll look at that later. This is why it's good to understand the math, at least to a decent extent, all right? So we need the measurement of risk. This is the convention. Variance of each asset is what we're going to use. And the variance is basically the difference between that asset at some time and the expected value or the mean value. And since you have an expected value of this, the variance is just a definition. It's defined as this difference multiplied by itself. So that way you have, no negative values, basically. You can't get a negative when you multiply two things that are the same thing. Two negatives will result in a positive. Two positives will result in a positive. So it's always going to be positive for that specific asset. All right. So then you take the expected value or the pretty much average of that. And when you work out this calculation, I'm not going to do it in this intro video, but I will in the series, you get this. The expected value of the asset squared minus the square of the expected value of that asset. So that's going to be for each asset. So as you can imagine, you do that for every single asset you own. Okay, you're going to get the fluctuations. These formulas arise out of the mathematical axioms and the laws of different properties, distributive properties and stuff like that. So that's why when you see these formulas, you might think, that's odd. Where did that come from? Well, it comes from someone trying to think about how markets behave and what's a good measurement of variability, and then using the laws of math. And that's where you get mixed up stuff. Okay, this is where you get issues, and these are the assumptions you put into your models. Like if we were just done right here, our model would be expected value and then variance, and we could subtract the variance or something like that, or try to minimize the difference between the variance and expected value looking at a time period. But that's where these weird, goofy formulas come from. They come from someone making assumptions, creating some stuff, and then using the laws of math. And like I said, just because it's math doesn't mean it's right. It's right as a math proof, but it doesn't mean it coheres or adheres to reality. Okay, and we'll get to that. I'm getting ahead of myself. All right, so now we have basically almost all the stuff we need to start thinking about optimizing this portfolio. We've got the expected return we're thinking we're going to make. We've got variability. But now we want to take it a step further with some idea of difference. Like I said, a hedge position. So if some asset goes down, like your biotech stock, and you want some other asset that's going to keep going up for that thing. When that goes down, you want something that's going to keep going up, gold, silver, whatever, or stay the same at least so you don't lose money and they both drop. That would happen possibly if you're in like a technology sector, totally. All right, so then this idea of diversification really starts forming, and we create this thing called covariance. Again, another definition. Someone has defined covariance as the expected value of the difference between each asset and their expected value times each other. And so you're going to get some kind of goofy formula, and then they're going to use math to, generalize that formula and to work it out. And then you get the covariance of all of the different assets. Again, not going to go into super detail on how to calculate this stuff, but in this video, but I will in a future video. So now, specifically, I have mentioned Wealthfront because I used them when I started investing, and I think it's a decent platform for people to get their feet wet and start investing without, initially losing a ton of money. Investing, I think, is a long-term thing. So yeah, the markets are going to go down. Your portfolio is going to lose money. But if you just leave it in there, this type of behavior should kick in and help you possibly mitigate losing money and hopefully make money. All right. And that's another thing. Investing's a gamble. Okay. I'm talking about the math of it, but don't invest if you don't want to lose your money, because you could lose your money. It doesn't matter what math you have or what math you use. You could always lose your money. No one knows the future. All right. Except Laplace's demon, but that's another video. All right. So we've got this idea of covariance where the assets fluctuate. Hopefully one goes up and the other goes up too. But then if one goes down, then the other can keep going up. That's that issue, that idea of covariance. How do they measure it? If you graph covariance of two assets, then you would hope to see something that is like a random scatter plot, or even like a little bit negative correlation. So that means like if one's going down, the other is going up. Okay, so then we pretty much have everything we need, except we have one more bullet point down here. I was going to say Wealthfront. So Wealthfront, I use them. They use 11 asset classes, which are defined in their white paper on their website. I'll post a link in the description. But they use all ETFs. So that introduces like an ETF risk, which you can't really, it's hard to measure with just variance, so you're not getting the whole picture. Everything has risk. There's multiple classes of risk, what you can use to lower risk and this and that. And modern portfolio theory really tries to lower risk using diversification, but you can only lower the risk so much. You've reduced your diversification risk where you're not invested in one thing, so you're hedging yourself in different positions, but it's kind of like insurance. And so, you wouldn't expect to make a ton of money hedging yourself, because you're going to be losing money, based on those hedge positions, but hopefully the net is a profit. Okay. So then this last thing, correlation, and that's basically, we have everything we need. The covariance is going to tell you basically if it's positively or negatively correlated, but it doesn't really tell you how much, that strength, and the correlation is going to tell you that. Again, I'll go over this formula in a different video too. Now we're at the fifth step. Okay, we've got this optimization problem that we've thought of. We're geniuses. We thought, you know what? We want to maximize our return. So one way to write that would be with all these goofy symbols. So we want to minimize something. What do we want to minimize? The difference between how much our return is going to vary, pretty much, given some level of risk. So all of these things, the W's are the weights that we're familiar with, the whole weights of the portfolio. So 10% in this, 20% in this, whatever. It's going to be added up to 100%. But these are matrices, which are just, it's like an Excel spreadsheet. You have rows and columns. And it's just a nice, easy, compact way to do different operations and solve different like linear equations, okay? So we need to do something because of matrix multiplication rules. We need to transpose the matrix. We'll have a column of it. And I know this is going to go beyond most people's heads who are not familiar with linear algebra and stuff like that. But this is what we could come up with, a formula. And then if it's important to know the parts of the formula. So we've got the weights. This is the covariance matrix. So all of the different covariances, and the weights again, just because that's how it works out in the linear fashion, you need that. And then we're gonna subtract our expected returns. And since we're minimizing this whole thing, we could maximize expected returns and by minimizing variance. So it just depends. And that's what modern portfolio seeks to do. They look at different risk tolerances, like, 10, 15, 5, whatever. They plug it into a formula that's very similar to this, and then they use a solver that solves for the lowest risk, the highest return for the lowest risk, excuse me. So with this optimization problem, we have a bunch of assumptions, that, okay, for this to work in reality, it can't just be, okay, we showed mathematically that this would be this and that would be that, but that's where the assumptions come in. You have to assume something about the variance. You have to assume something about the expected value in order for it to work in a real life setting, and also in order for it to work in a mathematical function setting. Like if you want to prove that this equals something or is going to maximize or minimize your value, mathematically prove it, you have to have a set of criteria so you can use those criteria to build your proof. But in the real world, that criteria might not work, so your model would not work as well. I mean, critics of modern portfolio theory think it is just absolute garbage. But the whole point of this video is to show you the math behind it and not really give a lot of my opinion on it. It's not an opinion video. So then the assumptions, we have those mathematical assumptions that you need to make to use the axioms and the laws of math to make this valid mathematically. But then we have the assumptions to work in reality. And to looking at this equation, we have to assume that the expected value, like we had over here, is a reliable measure for the underlying asset for like a future projection. And you see all the time on different securities websites that historical data is no measure, historical performance is no measure of future performance and stuff like that. And that's because, well, it could be random and you could lose money, and if they say that and they get sued and all that. So these things are important to know. So the expected value might not be reliable. It might not be a distribution that's super nice to work with. It might be a crazy distribution, a power law distribution or whatever. And the variance cannot be infinite. When you have time series data, pretty much an optimization problem, you have time series data. And any historical data, you have data points in time. All right, so the variance in that situation is going to it can't be infinite, because if you look at the variance calculation, you're using the data points, all right? So you arise an infinite variance in mathematical constructs, okay? In historical data, you can't. So the next data point would be all variables, or the bullet point, excuse me. All these variables in this thing can change, meaning that, you need to take a snapshot, 5 years, 10 years, 15 years, 20 years, 1,000 years, or however long the assets have been around that you're looking at and that there's data for. And then you calculate this stuff, because it doesn't automatically tell you, like, you're going to solve for something in this equation. You're going to solve for the amount of weights you put in each asset. That's generally what people do. So then if you're solving for that, well, you pick a time period and you fix your covariance variance matrix, and you pick your risk tolerance, so you fix that variable, and then you pick since the time period has been chosen too, well, that's going to have some specific calculated expected return. All right, so all of the variables can change. And so modern portfolio theory, boom, it selects a time period or a ideal measurement of this stuff, which right then there, you can see it's like risky right away. You see that might not hold up. That might not work. The expected value might be garbage. It doesn't consider the current situation of things. It just considers the historical stuff. So, but that's all we have for most math models. You can build in current situations, but again, it's all going to be assumptions. All right. So boom, we have hopefully built this intuition of the underpinnings and the under the hood of modern portfolio theory. I am not fantasizing that this video is going to be like all you need to know about modern portfolio theory. There's whole classes on it at MIT and Harvard and blah, blah, blah. whole lecture series. There's a lot of intricacies. But hopefully, like I said, this gives you the general intuition where this could arise, modern portfolio theory. And in the upcoming videos, we're going to look at assumptions of modern portfolio theory specifically, because this is an optimization problem. Modern portfolio theory is framed differently, and it has constraints like, maximize your value to this and that. We're going to look at the assumptions of modern portfolio theory using Harry Markowitz's paper and stuff like he won a Nobel Prize for. And, and people like to tout the Nobel Prize thing, and it's like, it's cool, yeah, it's great, but that doesn't automatically mean that it's going to work. Like, okay, it's a Nobel Prize, that's awesome, but does it match with reality? And that's when we get into the back testing and different types of simulations. We can like Monte Carlo simulations and different simulations of different time periods to see if modern portfolio theory holds up as a general theory. And if it doesn't, well, you got to make new modern portfolio theories like the Black-Lippmann model and different types of things. But we'll get into the math of all that. Thanks so much for watching the video. If you made it this far, you absolutely need to click that thumbs up button. Leave a comment. Let me know what you think. Have you even thought about modern portfolio theory? Is this all new to you? And are you new to investing, new to math, new to any of this stuff? Drop a comment below. Send me a message. Let's chat. Subscribe to the channel. Have a great day.